Okay, good afternoon. Maybe let us start our lecture. First of all, just to remind you that our midterm test is coming. It will be held next Tuesday evening, 8 o'clock, right? In the multipurpose sports hall. All right. We'll upload a sitting plan, so you will sit according to the sitting plan. We're still working on it. All right. So once it's ready, we'll upload it to the Luminous as well as IVLE. All right. Okay. So before the recess week, the last lecture we covered about John distribution. Now, John distribution means that we have considered two random variables or two or more random variables at the same time, and how they behave jointly. All right. So once you have the John probability function or John probability density function, you know everything about how this x and how these random variables behave jointly. Remember, when we say behave jointly, it means that for a particular outcome of the experiments, we consider two aspects of the outcomes. Or a particular individual or units being chosen, we look at two characteristics or more characteristics of these units or individuals. So what we continue today will be the talk about marginal distribution as well as conditional distribution. These are not new things. If you treat what we learned in chapter 1 about events, so this basically is the conditional probabilities as well as the marginal probability. All right, so okay, so marginal probability distribution. So it's about let's look at the two-dimensional variable, discrete or continuous. It doesn't matter. So with the John PDF or John probability function being f of xy, all right, and the marginal distribution is given by, for discrete case, all right, there are either a marginal distribution of x or marginal distribution of y. And what we are saying here is that, okay, if I'm only interested in x, so for given little x, I have to evaluate its probability. That is, I'm looking at probability of x equal to little x. So I want to get this probability from the John distribution, f of xy. So compare, okay, this means probability of x equal to little x and y equal to little y. Now, compare with these two expressions, they are not exactly the same. All right? Because for the John probability function, we have to specify x equal to little x at the same time y equal to little y. So they are more stringent. While this one, I did not specify the y value, the random variable. What is the value for the y random variable? What does it mean? It means that we don't care about it so long as those outcomes that give us random variable x equal to little x, I will consider it. So in other words, I need to add up all the probability with the same x value equal to the little x. I don't care about what is the y, so long as the x value, the random variable x equal to the little x. So I have to add up all this probability with different y values, but with the same x values. All right. Similarly, the marginal for y, I'm interested in the value of the random variable y equal to the little y. So I have to sum up all the John PDF with the same y. And for different x, so I just collect all those probability with the same y and add up all. All right. So the same idea extended to continuous case. So instead of doing summation, we do integration. So you may just treat for continuous case, we do the integration instead of summation, because integration can be considered as a summation. if you learned integration is just a Riemann sum. I mean, one aspect of looking at the integration is there is a Riemann sum of the function. So here I have to sum over all the joint density function over y. So I have to integrate y. All right. So remember, when we talk about marginal distribution of x, we're interested in only the random variable x. Then how about the other variables? How to get rid of it? No, we don't get rid. We just sum them up or do the integration to get rid of the random variable y. So I do the sum if it is discrete random variables and do the integration if it's continuous. All right, so similarly for the y, marginal of y. Now, let's look at this example. All right, so here, so according to the definition, okay, we look at this example on page 315. All right, so at f of x when x equal to 0, so I have to add up all the f of 0, 0, 0, f 0, 1, f 0, 2, and f 0, 3. So all the x, all right, are at x equals 0. But then y change from 0, 1, 2, 3. So I add up all this. How about 4? 5. Yes, we're supposed to add up all the possible y value. But what are all these probabilities? They are all zeros. Okay, let's look at the 315. 315. Here. Okay, so this is the okay, so this is the joint distribution. So if we want to calculate the f of x, okay, we have to calculate f of x for all the x value. So in this case, I calculate at x equals 0. So I have to sum up all these probabilities. All right. So the answer is 0.05. So in other words, f of x at 0 equal to 0.05. And f01, I have to add up all this probability because all these probability are related to x equal to 1. All right. So you cannot just take some of them. You have to take all of them. So add up all this. So this is f x evaluate at 1. Similarly, if I want to calculate the marginal of y, then for a fixed y value, I have to add up all this probability with different x value. So this is f of y evaluate at 0. All right? When y random variable takes the value 0. So that's why we call it marginal. So this is at the margin of this joint table. All right? Marginal. So you just look at one part of it. All right? We don't look at all the entries of this two-way table. We just look at the margins. Either the right margins or the horizontal, the vertical margins or the horizontal margins. All right? Oh. Okay, so this is for f of x for 0, and you have to compute for all possible x value. So for f of x, when x equal to 1, when x equal to 2, and so on. So this is the marginal distribution of x. Now, this marginal distribution of x, f of x, must satisfy the definition of a probability function, which means that all these entries must be bigger or equal to 0. And the sum of all these probabilities has to equal to 1. All right, so these are the two main properties about a probability function. All right, then how about f of x 6? What is this? What is the probability of x equal to 6? 0. How do I know it's 0? Looking from the John density function. Oh, sorry. Recall, you look at this. All right. So you can see that there are no x equal to 6. All right. So which means that the probability, the John probability of 6 and y, this is equal to 0. It doesn't matter what your y is. All right. So long as it's outside this range, 0, 1, 2, 3, 4, 5, then the John probability is 0. So hence, you sum over all the possible y. You basically sum over a bunch of 0. So this must be equal to 0. So that's why f of x for 6 equal to 0. All right? So this is the results that you have to understand. So marginal distribution, again, is a distribution. And in fact, the marginal distribution should not involve any y anymore. Okay, this is how you got the margin of y. So this is the final table that shows the John distribution as well as the marginals. All right? Okay, let's look at another example. So this example is for continuous random variables. So f of xy have a John PDF given by this formula. So long as x is between 0 and 1 and y is between 1 and 2, then the John distribution or John density function is given by this expression. Outside it, it will be 0. So what is f of x and f of y? So for x between 0 and 1, then we try to integrate the John PDF with respect to y. The idea is to get rid of the y, so we have to sum up all the y's for a fixed x value. These x values are fixed. The integration is work on y, so y we try to integrate out, try to sum over the y. All right? But the John PDF only valid, only equal to this expression when y is between 1 and 2. Now you have to remember f of xy is equal to this expression only when x is between 0 and 1 and y is between 1 and 2. All right? So therefore, here I'm working on the marginal of x. So I have to specify x within this range. Then, all right, then the John distribution will equal to this expression so long as y is between 1 and 2. All right? So I do the integration. Now, this integration looks complicated, but you have just to remember x in this integration is a constant. We don't touch it. Leave it there. Treat it as a constant, just any number. All right? While y is the function or the variable that we are going to integrate. So this one you can consider as 12, 13 integrate 1 from 2, x squared plus xy dy. So this one is just a constant. So after you do the integration, is x squared y. Well, this one becomes xy squared over 2. All right? With y from 1 to 2. All right? So this is what we have. So then, now, remember, now you can substitute whenever you see y, you substitute 2, and then after that, you subtract this expression, or subtract it, a term which is substitute y equal to 1. All right, so in other words, 12, 13, all right, 2x squared plus half x times 2 squared, all right, and then minus x squared times 1, and then minus half x times 1 squared. All right? So you complete the integration, it will be like this. So what does it mean? It means that the John PDF, now after I integrate out the y, becomes a marginal of x. Marginal of x is equal to 6 over 13 x times 2x plus 3. And this expression is only valid for x between 0 and 1. Between 0 and 1. So I want you to remember, you are talking about, first of all, we're talking about marginal of x. So you have to understand all this work are valid only when x is between 0 and 1. Why is it between 0 and 1? Because the John PDF is non-zero only for x between 0 and 1 and y between 1 and 2. All right, so you have to specify over this one. So, of course, naturally you will ask, so what happens if x does not lie within this range, 0 to 1? Then the marginal will be 0. All right, for the outside, the range, the marginal is 0. Why? Because the John PDF is 0. Nothing there. So no matter how you do the integration, it's still 0. The marginal is 0. The second thing is that when you do the integration, remember the expression, the John PDF here, this John PDF is valid only, not only x between 0 and 1, but y at the same time has to be between 1 and 2. So that's why the integration limit is from 1 to 2 when you integrate y. All right? So this is the marginal distribution. So now here is the question. Is it a valid probability density function? So in other words, whether this is bigger or equal to 0. Is it bigger or equal to 0? Always? No, we just need to, within this range, x between 0 and 1. That means if x is positive, then this expression is positive. So it satisfies the first characteristic of a probability density function. Second one, you have to do this one. Integrate from 0, in fact from minus infinity to infinity, f of x dx, whether it's equal to 1 or not, which is the same as integrate from 0 to 1, 6 over 13 x times 2x plus 3 dx, whether this one equal to 1 or not. So you have to check that. All right? Should be correct. If you couldn't get it, it means that you have made a mistake in your integration. All right, so for margin of y, so this time we have to specify y has to be between 1 and 2. Then you do the integration. This time x, you are integrating x, so x is from 0 to 1. Then this John distribution is given by this expression. So we complete it. And, all right, so the marginal of y, when y lies 1 and 2, is equal to this expression. Outside 1 and 2, it is 0. Now, it's important that when you complete the integration, the marginal of y, equal to that expression for y between 1 and 2. Nothing to do with x, because you already integrate out x. It shouldn't involve any x. The region will not involve any x, and the functional form of the marginal of y will not involve any x. Only involve only involve y for the marginal of y. So you have to remember that. So if you find that, after you integrate, you still have an x somewhere, then that must be a mistake. All right? Marginal of y involve only y for the functional form as well as the region. Marginal of x also involve only x, the function of x, and the region also involve x. All right? Okay. Then, conditional distribution. And this is a little bit more complicated, and in fact, this is very useful and very interesting. So, what is it? It's just record. In chapter 1, we learned probability of event A given event B. So it's equal to probability of A and B divided by probability of B. All right? If you recall, this is the definition of conditional probability. So intuitively, it means that, okay, we look at if event B has occurred, what is the chance of event A occurred? All right? So in that case, we because we know B has occurred, so we now reduce our sample space to this B instead of looking at all possible sample points S. All right? So then we look at those common to A and B and take the ratio of these two probability. That is the conditional probability. So for two random variables, we also have similar idea. So we are interested in finding how one random variable, let's say Y, behaves when we know that X, the random variable X, equal to certain values. So in other words, we are interested in this. What does this mean? This means that I'm looking at how the random variable Y behaves when X, the random variable X, equal to certain value. All right? Now, so in this case, this random variable X is no more a random variable because it takes the value equal to lead to X. Only Y is the random variable. So this conditional distribution is still a distribution of the random variable Y, the one that I wrote down there. All right? But it's conditioned on X. So it's different from this one, not necessarily the same. All right? The conditional distribution is at how random variable Y behaves when the random variable X equal to certain value. While the marginal distribution of Y is when looking at Y, disregarding what the X value is. All right? So these two are usually different. They can be the same. That is when random variables X and Y are independent random variables. That is a very important characteristic. When random variables X and Y are independent, then these two distributions will be the same. That means the behavior of the random variable Y does not depend on X. No matter what your X is, it behaves the same way. So that in that case, we say X and Y are independent. All right, so here is the definition. All right, compare with probability of A given B is equal to probability of A intercept B divided by probability of B. So it's exactly the same. So here is the conditional distribution is equal to the ratio. Numerator is the joint PDF. How X and Y behave jointly. It's like a probability of A intercept B. It's the joint behavior of these two. X equal, this means that if I restrict to the discrete random variable, this is something like, for discrete, I have to emphasize, for discrete random variable is equal to this one. The numerator, the denominator is X equal to X. All right? So you can treat this as event B, this is event A. So it's probability of A intercept B. That means both A occur and B occur, and then divide by probability of B. This is only for discrete case. All right. So conditional distribution is to look at the joint distribution adjusted by the marginal distribution of X. Because you are conditioned on X, so it is adjusted by the marginal of X. Provided that the denominator is not 0. It has to be bigger than 0. It cannot be 0. All right. So what does it mean? Intuitively, it means that if this equal to 0, that means the random variable does not equal to this little x. Then how can you condition on something that is never occurred? So it does not make sense. So we only consider the f, in this case, f of x is bigger than 0. So similar definition. So this is for x within the range of, for any x within the range of the random variable x. All right? And for y, it's the same thing. So condition on y, all right, so it will be the joint PDF divided by the marginal of y. given that y is bigger than 0. Now, here is something special about this conditional distribution. From the distribution point of view, the conditional distribution is a distribution for random variable y. This one. Oh, sorry, for x. All right. This is the random variable. We are talking about this random variable. Now, how about the y? The y already fixed. It's no random variable. It's equal to this lead to y. We have already have this value, right? It's conditioned on y equal to the lead to y. All right. So my point is, conditional distribution is a distribution of the random variable on the left side of this vertical line. This is the random variable of x in this case. This is the random variable y. But the expression, this one, is a function of x and y. That means you may see the other quantity, this y, because it's conditioned on y. So this may be a function of x and y together. I don't want to write f to confuse you. I just want to say that mathematically, this expression, all right, may involve both x and y. Okay, let's look at them. Okay, so because it's a distribution, so when you sum over x, it has to be 1. Sum over y for the conditional of y given x has to be 1. Because the random variable we are talking about is y, so you sum over y has to be 1. So similarly for the continuous random variable, when you integrate the random variable x with respect to x is equal to 1. Integrate the conditional distribution of y given x with respect to y, it has to be 1. Okay? So, and we just make use of the formula. We just multiply. Remember, it's supposed to, this one, so I just move this to the other side. So it becomes the John distribution be expressed as a product of two factors. The first one is how x behaves alone, marginal of x. Then the second term, the second factor, is how y behaves given x equal to the lead to x. So the product of these two will give you the John probability density function. All right? So it goes both ways. Usually, maybe we start with everything we know the John distribution. So we are given f of x, y, the John distribution. Then we can calculate the marginal, we can calculate the conditional distribution. But on the other hand, we can also have just the marginal of x of one of them, like for example x, and the conditional distribution of y given x. Then we multiply them. We'll get back to the John distribution. Now how about this? I know f of x. I also know f of x given y. Can I multiply these two to get back the John distribution? Can I? No. This one is how x behaves. This one is how x behaves given y. And no, you cannot multiply these two to give you something meaningful. All right? It has to be, because this formula comes from this definition of John distribution. This, when we look at it, it is the John distribution of x and y together, and then adjust by condition on the x, so I adjust by x. So I move this to the other side. So it looks as if I check x equal to lead to x, how it behaves first, and then check y given x, how it behaves. All right? So, similarly for the f of y. Okay, let's look at examples to see. Okay, now suppose I have experiments. I toss three tosses of a fair corn, and the outcomes are equally likely. So the outcomes is like this, like head or H tail head, something like this. All right, these are the outcomes. So now I define the random variable x is the number of heads on the last flip. So I'm only concerned about the flip, the number of heads. So it's either 1 or 0. If the last flip, the outcome is like this, for example, or like this. So the last one is a tail, so the number, so x equal to 0. This case, x equal to 1. While y represents the total number of heads for the 3 tosses. All right? So it can be y. So x is 0, 1. Y is between 0, 1, 2, and 3. Right? 3 tosses, you get 3 heads. 3 tosses, you can have 0 heads. Right? This is the total number of heads. So find the conditional distribution of y given x equal to 1. So in other words, if we know that x equal to 1, x equal to 1 translated means that if we know that the last flip is a head, then what is the chance, how this random variable y behaves? All right? Conditional distribution of y. I want to know how y behaves. All right? So, first of all, I work out the John PDF. So this is the John PDF, f of xy. How? So I work out, these are the outcome. So these are the outcome of the sample space. So for this outcome, x equal to 1, y equal, for this outcome, x equal 1, y equal 2, and so on. So now I put it down the John distribution in book. So in that case, x equal to 0, y equals 0, which is this one, so it's 1/8. When x equals 0, y equals 1, there are 2 of them, so I have to add up these 2 probabilities. Because x equals 0, y equals 1 is equivalent to this event in terms of random variables. It's equivalent to THT and HTT. So these 2 are equivalent events. All right? The random variable x equals 0, y equals 1 is equivalent to THT and HTT. So we have to add up these 2 probabilities, so it's 1/4. So that's how we construct the John probability function for this example. And these are the marginals. So f of x equals 0 is half, f of x equal 1 is also half. Then for f of y equal to 0, the chance is 1x, y equal to 1, it is 3x, and so on. So these are the marginals of x, and this is the margin of y. So now, if we know that x equal to 1, what does it mean? It means that we are now concentrate on this row with x equal to 1. So it involves the outcome x equal to 1, y equal to 0, x equal 1, y equal to 1, x equals 0, y equal to 2, x equals 0, and y equal to 3. Involve all this. So the probability will be the John PDF divided by half. All right, so the conditional distribution of y given x equal to 1. All right, so it will be like this. When y equals 0, this one is 0. When y equals 1, it will be 1x divided by 1/2. The John distribution divided by the marginal of x. When y equal to 2, it is 1/4 divided by 1/2.
When y equal 3, it is 1x divided by 1. All right, this one is 0 divided by 1/2. All right? So now the marginal will be 0 divided by half is 0. This one divided by half is 1/4. This one is 1/2. And this is 1/4. So this is the marginal. So what does it mean? It means that if we know that the last flip is a head, then the total number of heads must be at least 1. Because the last one is a head. All right, so it cannot be 0. So you can see that. So this one is, when y equals 0, is impossible. All right, so this is the marginal, sorry, the conditional of y equal 1. So how about if x equal to 0? X equal to 0. Then you are looking at this line. So you have to divide the joint distribution by the marginal of x, which is half. So in other words, for f of y given x equal to 0, it will be 1x divided by 1/2, 1/4 divided by 1/2, 1x divided by 1/2, and 0 divided by 1/2, corresponding to 0, 1, 2, 3 values. So again, you can see that if we know that x equal to 0, that means the last flip is a tail. You cannot have 3 heads, at most 2 heads. So you can see that the conditional probability of y equal to 3, when x equal to 0, it is 0. All right, it is 0. So that's how we understand about the conditional distribution. All right, so this is show how you got all this. So this is what we have. And then you notice that every entry is bigger than 0, bigger or equal to 0. And when you sum them up, it's equal to 1. All right? Then how about f of y given x when y equal 4, given x equal to 1? What is this? If you know that the last rate is 1, how can you got 4 heads? We have only 3 toasters, so this is 0. Right? So what I mean is that outside this 0, 1, 2, 3, in fact outside 1, 2, 3, the conditional probabilities are all zeros. Okay, here's another example. Okay, referring to 312, example 1. So this is the joint probability function. All right. Now this one you can write down in a table form, because x has only 3 possible values, y has 3 possible values. So altogether there are only 9 possible values for this joint PDF. But maybe you also have to get used to express the joint PDF in a functional form, in a mathematical formula. Okay, this is valid for x equal 1, 2, 3 and y equal 1, 2, 3. So in other words, if I have f of xy for 1, 1, then x equal 1, y equal 1, it will be 36 times 1 times 1. This is the probability of x equal 1 and y equal 1. How about f of xy 1, 2? Then it will be 1 over 36 times 1 times 2, y equal to 2. So this will be 2 over 36. So this is how we understand about this expression. All right? So find the marginal of x and use that to find the conditional distribution of y given x. All right? So how to do it? So to find the marginal of x, we have to sum all the y values for a given x. So we sum y from 1 to 3, 1 over 36 f of x, 1 over 36 times x times y. Now, we are summing 3 terms. The terms is represented by this. So what this whole thing means is that we are summing up when y equal 1, we are summing up this. When y equal 2, we are summing this. Y equal 3, and y equal no 4. So basically we are summing this. This is just a way to write down this whole expression. All right? But you notice that every term, there are 3 terms there, every term has 1 over 36, x over 36. So I bring this out as a common factor. So what left behind are those y. So I take this out. So take this 1 over 36 times x out of the submission sign. So I just sum over the y from 1 to 3. So basically sum 1, 2, 3. All right, so that's how you do it. So it's equal to x over 6, where x equal to 1, 2, 3. And if x does not equal to 1, 2, 3, the f of x is 0. All right? Okay. Is this positive? Yes. Bigger than 0 for x equal 1, 2, 3. And you sum up all the f of x, where x equal to 1, 2, 3 is equal to 1. Because it's just 1, 6 plus 2, 6 plus 3, 6 is equal to 1. Okay, then how about the conditional distribution? Now, so here I specify that for x equal 1, x equal 2, or x equal to 3, I can apply this formula. All right? It is the John PDF, because for x equal 1, 2, 3, the John distribution is given by xy over 36. And the marginal distribution is given by x over 6. All right? So we do some cancellation and left with y over 6. And this is a function of y. This is a random variable of y. And the expression, all right, y over 6, and valid for y equal 1, 2, 3. It's interesting, huh? Just now I keep telling you that this is a random variable of y. But the expression can involve x. But in this example, the x is not seen here. In other words, after you calculate the conditional distribution, some cancellation occurs and it does not depend on x anymore. So what does that mean? It means that it doesn't matter what your x value is, so long as x equal to 1, 2, or 3, then the margin, that means given x equal to 1 is equal to y over 6 for y equal 1, 2, 3. All right? Given x equal to 2 is also y over 6, y equal to 1, 2, 3. Given x equal to 3, it is also y over 6 when 1, 2, 3. F of yx, y given 4, it's no more y over 6, huh? It's 0. Because John PDF does not equal non-zero when x equal to 4. So this equal to 0. So my point is, in this example, the conditional distribution supposed to be the condition of y given x. So it's only concerning about the random variable y, one random variable. But the expression can be a function of y and x. But in this example, it's only a function of y. It does not depend on x. So what does it mean? It means that for any x value, so long as it's 1, 2, or 3, then the conditional distribution are the same, which means that it does not depend on x. And what does it mean? It means that we don't care or what information you know about x, the random variable, does not help or does not change your belief in the behavior or in the distribution of y. So x and y in this case are independent random variables. All right? Here's another example, but for the continuous distribution. All right? So the John PDF defined over this rectangular area, x between 0 and 1 and y between 0 and 2. So we find the marginals and find the conditional distribution. So we just do the integration. So for the marginal, whenever x is between 0 and 1, why we consider this one? Because only when x between 0 and 1, the John PDF is non-zero. So then we integrate y. The y supposed to be from minus infinity to infinity, but the John PDF is equal to 0 outside this range. This means that when y equal between 0 and 2, the John PDF is given by this expression. Then we continue to do the integration, and the answer turned out to be this one. It's a marginal distribution of the random variable x, and it should not involve any y, any other random variable. Not the random variable, not the value. So you shouldn't see any y there. Okay? But this one is a function of x, and this one also you have to specify the range of x for which this marginal distribution equal to this expression. It's important, you must specify this. All right? Without this one, how do I know that this is equal to this? Is it true for all the x value, even x equal to negative number, or even x equal to 10, 20? No. It's only valid for x between 0 and 1. So in other words, f of x is equal to this expression when x is between 0 and 1, and with 0 otherwise. All right? So in other words, integrate from 0 to 1 of this expression over x, this should equal to 1. Should equal to 1. All right? Outside that range, the f of x is 0. So similarly for the y, all right? So this is the answer, the marginal for x. So similarly for the y, so I have to specify the range of the y for which the PDF of the marginal of y is given by this expression. All right? Okay, so here is the results, the marginal of y. All right? Now, how about the conditional distribution? Now, I want to calculate the conditional distribution of y given x. All right? The conditional distribution of y given x. That means we are talking about the random variable. The random variable we are talking about is y. Y is the random variable. X is not a random variable. X already specified equal to a particular value, which is little x. All right? So by definition, it has to be like this. The condition of y given x is equal to the John distribution divided by x. Make sure the denominator, those involved, we're talking about the marginal of this, the expression on the right hand side of this line, this stroke. All right? This x, so this is the marginal of x. Condition of x, so the denominator is the marginal of x. All right? So this is the John PDF. This is the marginal of x. So we divide it. So it's equal to this expression. And this is valid for y between 0 and 2. All right? Now, let me repeat it. This part is the marginal. It's valid for any x between 0 and 1. All right? But this part, the John distribution equal to this expression, is valid only for x between 0 and 1, and at the same time, y has to be between 0 and 2, because that is the region for which the John PDF is defined, given by this expression. This is the f of xy, and only valid for this x between 0 and 1 and y between 0 and 2. All right? So therefore, this expression is valid only for x between 0 and 1 and y between 0 and 2. And after we simplify it, it's like this. So you can see that the conditional distribution equal to this expression, which involve x and involve y. Right? Do we understand this? Remember, x is fixed at little x. So these are fixed. These are fixed, are constant. So once you have this value, you substitute in. Here we just denote it by little x. So these are constant. So treat this whole expression as a function of y. How the density behaves for y, all right, is treated as a function of y. All right. So once x is given, we can substitute into this place, like x equal to, let's say x equal to 0.5. Then I can substitute 0.5. All right. So in other words, if I want to know when x equal to 0.5, how does the random variable behaves? Then this is equal to what? 3x, right? 3 times 0.5 plus y over 2 times 3 times 0.5 plus 1. All right, so it's 1.5 plus y, 1.5, 2.5, so it's 5. Am I right? For y between 0 and 2. So this is how the f behaves when x equal to 0.5. When x equal to 0.7, then you may substitute this as 0.7 and then try to evaluate it. All right? So it still depends on your y value. Okay? Okay. So when x equal to 0, this is the conditional distribution. And when x equal to 0.5, 3 plus 2y over 10. All right? So you have to understand when we talk about conditional distribution of, let's say, y, condition on x, your expression involves x and y. What it means is that when you given x, you substitute the value of x into the expression, then the whole expression will be left with only the y. So as you can see that when x equal to 0, the conditional distribution is y over 2. When x equal to 0.5, the conditional distribution is 3 plus 2y over 10. Now you can see the two conditional distributions when x equals 0 and when x equal to 0.5 are different. They're not the same. What does it mean? It means that x and y are not independent. All right? The information, knowledge about x will give you a different view about the behavior of the random variable y. All right? Okay, so similarly, for the conditional of x given y, all right? So this one is valid for y between 0 and 2, and then you try to work it out, and this is the expression for x between 0 and 1. So now, for particular, if you substitute y equals 0, then the behavior of x will be 3x squared. While if you substitute y equals 0.5, then the x will behave as the marginal distribution of x when y equal to 0.5 is given by this expression, which again is different from this one. These two are not the same. So you can see, you also support what x and y are not independent. All right. So here's another example. All right. X is the proportion of time for a driver facility being used, and y is the proportion of time that walk-up window is in use. And all this XY pair referring to a particular outlet. All right, the same outlet. So the joint PDF is given by this expression. All right. Then find the probability that neither facility is busy more than 1/4 of the time. Okay, neither. Then simply means that we are finding the chance that the x is less than 1/4 and y at the same time y less than 1/4. All right. So you must translate the question into a probability statement involves the random variable x. So it say that neither facility is busy more than 1/4 of the time. Okay, so cannot be more than 1/4 of time for both facilities. So it's x less than 1/4 and y less than 1/4. And Okay, then find the probability distribution of X without reference to walk-up time, what happened to the walk-up window. So in other words, we don't care about what happened to the, so we just look at f of x. All right. Then find the probability that a drive-up facility is busy more than 1/4 of the time, but less than 3/4 of the time. So in other words, we look at x less than 1/4, bigger than 1/4 and less than 3/4. All right. We only concern about x. We don't care about the y. Then the third question, given that the driver facility is busy 80% of the time, what's the probability that the walk-in facility is busy at most half of the time? All right. Now, so this one concerned about x equal to 0.8. Then what happened to the y? All right. So we are given the information, given that x equal to 0.5. Now, don't confuse. We are talking about fixed x at certain value. All right. So x, although it's continuous, but x can take the value equal to 0.8, 80%. Then what is the chance that y less or equal to half? Okay, so given that x is 0.8, what is the expectation of y? All right, because y is a random variable, one dimension random variable. So we can talk about the expectation. All right, so here it is. So the first one, we have to integrate the John PDF from 0 to 1/4, 0 to 1/4 for x. And then after that, after we complete the first integration, or the inner integration, then it will be a function of y. Then y is integrated from 0 to 1/4. All right, so this is how we do it. Here I just take out the 6/5 and then integrate x and then plus integrate y squared. So after we complete the integration, it turned out to be 7/640. All right. So okay, this part you take the 6/5 out and then break down this sum of these two. I integrate x with respect to x and y, integrate y squared with respect to x and y. So when I do this integration, what I got is x squared. This becomes x squared over 2. And substitute x, because we're talking about integration of x, so x equals 0 up to 1/4. Similarly, when I integrate y squared, treat this as a constant. So it's y squared times x, y squared times x. And then substitute x equals 0 to 1/4. So now I substitute x equals 0, substitute x equals 1/4 into this expression, find the difference, and so on. So I got this line. So I got this. All right. You can see that now I integrate with respect to y for this one. So what I got is y over 32. And substitute y from 0 to 1/4, the two limits. This one, it becomes y cubed over 3 and then time over 4. So it's y cubed over 12. Substitute y equals 0 to y equal to 1/4. So this is the answer. Very small chance. Then the marginal distribution of x, which means that you integrate over y, and y only valid from 0 to 1. So you do the integration from 0 to 1. Because the John PDF is valid for x between 0 and 1 and y between 0 and 1, right? Yeah. So after we complete the integration, it's equal to this. No more y, all right? Because all the y's are integrate out, so you substitute y equal to certain values. Okay, so marginal is equal to, margin of x is equal to 6 over 5 times x plus 2 fifths. And this is valid for x between 0 and 1. All right? Just a word of caution. Whenever you write down your marginal distribution or your probability function or probability density function, especially probability density function, the joint probability density function or the marginal probability density function or the conditional probability density function, you must write down the region for which the function equal to that formula, equal to that. You specify that. Okay, so in this case, the marginal of x is not equal to 6 over 5 times x plus 2 over 5, when x is outside the range of 0 and 1. It's only valid when x is between 0 and 1. And outside it, what is f of x? It's 0. But why is it 0? Why is it 0? Because the joint PDF that's given to us, the joint PDF is 0. The joint PDF equal to this expression only when x between 0 and 1 and y between 0 and 1, and 0 outside this range or this regions. All right? So I keep telling you, it's not just equal to this one, but you also have to specify the region for which this is true. All right? So for probability of x between 1/4 and 3/4, then I just integrate the marginal of x from x equal to 1/4 to 3/4. So quite straightforward. So the answer is 1/2. Alternatively, this is equal to integrate the joint PDF for y from minus infinity to infinity and x only between 1/4 to 3/4. All right? But if you notice, what is this? Integrate the joint PDF with respect to y. What do we call this one? The marginal of x. Right? So it is equal to 1/4 to 3/4 marginal of x. So it is the same thing. Of course, if you know that I'm going to find probability of x between 1/4 and 3/4, all right, this expression, this probability that we're looking at, involves only one random variable, x. Then why bother to work on this part if you have? This one involves double integration. If you have the knowledge about or the marginal distribution of x, then you just integrate respect to x over this marginal of x. All right? But what I'm saying is that this way to do things is equivalent to you do the joint distribution, but you integrate the y first, which will give you the f of x. This part is just f of x. All right. So C part, we are asked to find the conditional distribution when x of y when x equal to 0.8. So this is the joint PDF with x equal to 0.8. So I substitute x equal to 0.8. So substitute x equal to 0.8. All right. So simplified it, I arrive at this expression. So this is the joint distribution, sorry, the conditional distribution of y when x equal to 0.8. But is this valid for all the y values? What's the range of y for which the conditional distribution equal to this expression? It's only y between 0 and 1. Why? How do we get this range? Because this equal to this is valid only for y between 0 and 1. Not only that, x has to be between 0 and 1, but this is between 0 and 1, so it's okay. So this one is already okay. So this one you have to specify. From here, when you substitute this into, using this expression to replace this, to substitute this into the joint distribution, it's only valid when y between 0 and 1, so you have to keep it here. All right, and 0 otherwise. So, what is this? Shall we substitute this as 1.5? 1.5 instead of 0.8? No. X equal to 1.5 is outside the range. So the joint PDF is equal to 0. In other words, marginal is also equal to 0. So the conditional distribution does not exist. You cannot condition on something, some value of x, which is no chance to occur. You condition on something that will not occur. So it does not make sense. All right? So this one, no, not defined. All right? So my point is, don't just, oh, I got the expression, so I substitute it without checking whether it's valid or not. In this case, the form, the conditional expression, okay, equal to this one only when x is between 0 and 1. And this is only valid for y between 0 and 1. Outside that, it will be 0. Okay, so now I can consider finding this probability. So I just integrate from minus infinity up to half of the conditional distribution. But again, from here to here, this equal to this expression only for y between 0 and 1. So in other words, I have to break down this integration into two integrations. All right? This is equal to 0. Okay, the margin, the conditional distribution, all right, for y in the negative region is 0, while this is equal to this expression. So we just integrate from 0 to half, and the answer is 0.397. All right? Oh. Okay. Finding the expectation of condition, this I will call it conditional expectation. That means if you know x equal to 80%, 0.8, then what do you expect about the waiting time for being busy for the walk-in facilities? So this is the expectation of a random variable y. All right? To find the expectation of y, you have to integrate y times the conditional distribution of y given x equal to 0.8. All right? You have to integrate from minus infinity to infinity y. All right? We are asked to find the expectation of y, but this y is conditioned on x equal to 0.8. So I have to work on the conditional distribution of y given x equal to 0.8. All right? And this is equal to integrate from 0 to 1, y, what is the expression? 6 over 34 y, 4 plus 5y squared dy. Because outside this range, outside 0 and 1, the conditional distribution is 0. So, after we complete the integration, it is 0.57. What does that mean? It means that if we know we have two facilities for this outlet. One is drive-in, the other one is walk-in. Okay, the drive-in, we know that, okay, at this point, it's busy, for this particular moment, it's busy 80% of the time. All right, it's very busy basically, okay, 0.8. So what happened to the y? So it's described by that function, is how it behaves. This expression, how it behaves. All right, but then we would like to know, okay, what do you expect? So we expect it, if we know that the drive-in busy 80% of the time, then we expect the walk-in have a busy time is about 58 or 57% of the time. All right, so we expect it quite busy. So in other words, it can be higher, can be lower. On average, we expect 57% of the time. You can redo everything by looking at, for example, x equal to 0.2. That means the business is not good. The drive-in facility is only 20. Then how does the y behaves? At the same time, ask what do you expect about the percentage of BC time? So check. So repeat everything with x equal to 0.2 and then see what happened. All right. So what I did not ask, or you can do it yourself. Can we do this one? What is the variance of this random variable y? Given x equal to 0.8. So it's nothing new. You just work on the conditional distribution and substitute x equal to 0.8 in the conditional distribution. After you substitute x equal to 0.8, then everything is just a function of y. Then you try to find the variance of y. So usually you will look at this one first, y squared, and then minus the square of the expectation of y. Or in other words, minus the square of this number. Right? Okay. This one is a little bit technical about the integration part, but it's also is useful. Here, we define a random variable with a uniform density function over a range. All right, over a range. What is this range? Do I have a picture to show you? Here's the picture. The John PDF only defined over this range. All right. It's not a rectangular shape. So, it's defined over this range, x less than y. All right. So in this case, all right. So the x value is less than y, and y is between 0 and 2. So you can see that. Okay. How to identify this region? There are altogether 4 inequality. X bigger than 0, x less than y, y greater or equal to 0, and y less or equal to 2. Right? So, x bigger or equal to 0, so to look at this region, basically you look at x equals 0. So this is x equal to 0. This line is x equal to 0. X bigger or equal to 0 means that you are looking at this part of the line. And then y greater or equal to 0, basically you are looking at this part. So the intersection of this already means this quadrant. Next, y less than 2. So you look at the line y equal to 2. This is line y equal to 2. Y equals 0. X equals 0. All right? So this is the line y equal to 2. y less than 2 means that you're looking at this region. All right? Finally, x less or equal to y. So you look at the line, this line, y equal to 2. Okay. All right, so this line is y equal to x. So x less or equal to y means that it's this region. All right. All right. So you are not given the f of x, y. What is this? We are not given. But we are given that the PDF is uniformly the same. So I can call K. All right? It doesn't matter what xy value is. So long as xy value falls in this triangle, then it's equal to K. So that's why we have to work out. So obviously the area of this triangle, the height is 2, the base is 2, so we multiply and get the area equal to 2. So the area is 2 for this triangle. 2 times 2 divided by 2, so it's 2. So I have to integrate, all right, K. So this one, remember, this is the region, right? So I integrate x first. Integrate x first means that I have to fix y. Fixed y, I try to integrate from this point to this point. So at this point, x equals 0. At this point, x equals 0. At this point, x equal to y. So the limit is from 0 to y, k dx. And then after I complete the integration of x, it means that I squeeze all the density onto this line. So add all the density to this line. Of course, at this point, the density is smaller. At this point, the density is higher. So this one has a higher density. So after I do all this, then I integrate y from 0 to y equal 2. That means I sum up all the density here. So after I complete all this integration, it's equal to 2k. And this 2k must equal to 1. All right, because this simply means, this whole thing simply means that we are integrate from minus infinity to infinity the John PDF dx dy. And this has to be 1. And after I do the integration, it turns out to be 2k. So 2k must be 1, or k equal to half. So after I do all this complicated integration, I got k equal to half. But if I look at from a very simple way, very intuitive way, is that I look at this area with 2. And then I need to have to raise from the ground a height k, so that the volume equal to 1. So the height must be half. Half times 2 give me 1. So therefore, I need to raise the PDF to half. So the PDF is half. All right, after that, so this is my John PDF. Okay, then for the marginal, now it's quite straightforward. For the marginal, I have to integrate y, so it's the same thing, x from, okay, so I integrate y, so I fix the x, then y has to be from this point, y equal to x, and this point, y equal to 2. All right? Fixed x, I have to integrate, so you can think of it, all the density fall in this point. I squeeze from all the density, I have to squeeze it to this. You can think of it, I have two plane, I try to squeeze it into one, so that all the density here will be concentrated on this one. So all the density here will be concentrated here, and all the density here will be concentrated at this point, and so on. So that's how we do it. So after we complete the integration, it will half 2 minus x. for x between 0 and 2. Is it always bigger than 0 for this one? 2 minus 6. If x is bigger than 2, this is negative. But fortunately, x has to be between 0 and 2. So this is always bigger or equal to 0. Okay, similarly for y. For margin of y, that means you have to integrate x. So I have to integrate x, so I fixed y. So y equal to 0 up to, I integrate x, right? So x equal to 0 up to x equal to y. All right, x equal to 0 up to x equal to y. So 0 to y. And after you complete the integration, the marginal of y is y over 2 for y between 0 and 2. So with the marginal, we can compute the conditional distribution. So the conditional of y given x will be the John distribution. And this John distribution equal to half only when x between 0 and 2 and y. Okay, this one, we are talking about the conditional of y given x. So given x, given a particular x value, you are looking at this part. All right? Let me remember, you are talking about the marginal of y given x. So given x here, your John distribution is valid for this region. This region is with y equal to x up to y equal to 2. Therefore, y has to be between 2 and x for a given x. For a given x, y only valid, the marginal, the John distribution only valid equal to half when y is between x and 2. So if x is here, it's still between x and 2. All right, so y has to be between x and 2. And this is the marginal of x. It's valid for x between 0 and 2. All right? Now, the marginal of y given x is equal to the John distribution divided by the marginal. The John distribution equals 0 and equal to half when x between 0 and 2 and y between 2 and x. So for fixed x, so I fixed x. So long as x is satisfied this, okay, then I look at it. So I fix x, then the y is between x and 2. But if you fix x here, all right, then there's no more density over this part. So this is 0, it's not 1/2. 1/2 is only for this region, for this triangle, the area, from 0 to 2. This is also 2. Okay? So this is the marginal of y, the condition of y given x. This whole thing, all right, does not involve any y. It only depends on x. All right? So it's equal to 1 over 2 minus x, so long as y between x and 2. Now, what does that mean? It means that no matter what your y value is, the probability density function is 1 over 2 minus x. It only depends on x. So what does that mean? It means that it is uniform over this region. It's the same over this region. All right? Okay, so similarly, you can work out, okay. So here when x equal to 1.5, then I just substitute 1.5. So it is the condition of y given x equal to 1.5 is 2. All right? Okay, how about x given y? So x given y, so I have to look at this equal to this only when y is between 0 and 2 and x, all right, fixed y. So x at this point, x equal to 0 up to this point, x equal to y. So x has to be between 0 and y. All right. So long as y is somewhere here, y is somewhere between 0 and 2. Outside it, if y here, then this will be 0. All right? So divide by the marginal of y. So this is the answer. So again, you can see that the marginal of x given y does not depend on x. So it's uniform everywhere so long as it's between 0 and y. All right? And it depends on y. Given the y, then it's equal to 1 over y. So for example, y equal to 0.5, then f, the conditional distribution of x given y equal to 0.5 is 2. It's uniform. So long as x is between 0 and 0.5. This 0.5 is this 0.5. So you can check. So like 0.8, then this is equal to 1 over 0.8. All right? And for x between 0 and 0.8. And 0 otherwise. Okay, so this is how we interpret it. So now we want to find the probability of x less or equal to half when y equal to 1. Then we just integrate the conditional distribution of x with y equal to 1. So from minus infinity to 1, which is the same as integrate from 0 to half, with y equal to 1, it becomes, because this is 1 over y, right? If I remember correctly, 1 over y. So it's 1 over 1, so it's 1. So the answer is 1/2. So, this one had nothing to do with the conditional distribution. It's just the one that to find the probability of a joint event, x less or equal to 1 and y less or equal to 1. So integrate from 0 to 1 and 0 to y. Why? Because here I integrate x first. So I fixed y. So in other words, I look at this part. So I integrate x equal to 0. This point, x equal to 0. At this point, x equal to y. Because this is the line y equal to x. So at this point is y. And then after I integrate all this, that means all the density here falls onto this point. All falls to this point. So now I have density along this line. It is from 0 to 1. So it's integrate from 0 to 1. So the answer is 1/4. 1/4. All right? This is a simple way to do it, but you can check it. It's uniform, right? So you can see that it's 1/4. All this area are the same, and the density are the same. So you only have one part of these 4 parts. So it's 1/4. This is used for checking. It's uniform. It's nice to have uniform. But what I try to show you is through the hard work, and it applies to any distribution. It's not uniform, but given the joint distribution, you are able to do all this. The idea of this example is to illustrate how to get the integration limits. All right, you have to consider the integration limits. All right. So sometimes you draw a picture of the region that you are interested and then try to work it out. Okay, I think I have to stop here instead of starting a new section. So we'll continue tomorrow on this section as well as maybe chapter 4. I'll try to upload chapter 4 notes today or early.